So now that we have learned all the different triangle congruence methods, we're going to put it all together and actually use them in a proof. And I've got this packet of proofs, excuse me, from somewhere. It is not my own creation, but honestly, I got it so long ago I don't remember where I got it from. So if you happen to see this on the internet and this is your document that I have taken from you, please know that I am very grateful, and just send me an email and I will give you credit. I'll re-record the video and give you credit. This is not my own creation, but it's really well done, so I would like to know who did it eventually, who made it. So what we have here is, as we all know, a two-column proof, okay? But actually, I'm going to turn this around. This will work better this way. Gosh, excuse me. We have a two-column proof. Here's our diagram. We have a given. We have actually two givens right here. And we have a proof statement, and we have our two columns already set up with statements and reasons. This is really well organized. And in order to kind of break the ice as a baby step here, we have all the necessary reasons. So this is basically just like matching. We need to match up which reason here out of the 6 reasons given match up with which of the 6 places over here in the proof. So let's think about what this is saying. And so I want you to really be careful with the way that I'm going through this and paying attention to what I'm saying so that you can start to understand the reasoning behind how all of this works. So the first thing that I always do is take the given statements and I mark them. I mark them right on the diagram. So for example, YX line segment is congruent to WX line segment. So what that means is YX is this right here. So this line segment, okay, we're trying to show that that line segment is congruent to WX here and there, okay? Or excuse me, that is a given. That is a given. That is this, what I have marked in the blue on the diagram, okay? And we're also told that line segment ZX bisects angle YXW. Okay, angle YXW and ZX bisects it. So what that effectively means is that that is congruent to that, but notice that it's just telling us that it bisects it, and this is what I've written I've marked in the green right here. So notice that it's telling us that it bisects it, and then from this I can infer that what would this be? Angle YXZ is congruent to angle, so YXZ is congruent to angle WXZ. So I'll infer that in a step here. As you can see, that's actually step number 3. And so the reason we can't just jump to this is that we're not told that. We're told that it bisects it. Now we can do something with that word and we can say, oh, but ... that means this. It means this part, but we're not told that explicitly, so we have to deduce that using a step. So, and we're trying to prove, we're trying to prove that YZ is congruent to WZ. So we're trying to show that YZ, right here, we're trying to show that YZ is congruent to WZ. We're trying to show those two, and that is in the red right there. Okay? So, let's see what we've got. Well, YX is congruent to WX. How do we know that? It's a given. It's right there. It's given to us. So this is a given. Okay? And so we've used up one of those givens. ZX bisects angle YXW. And it's also a given. Okay? That's also a given. And usually I will combine all the givens into one step, but I like doing it this way at the beginning just so you see that, yeah, you're given two different things up there. And so that's step 1 and 2 right here. So then how can we say that yxw and wxz are congruent? Well, we said that right here. We infer that because we know that this bisects it. So it's the definition of an angle bisector that tells us that it splits them into two congruent angles, right? Now, xz is congruent to itself because of the reflexive property. Okay, anything is congruent to itself because of the reflexive property. And so what that is talking about, xz right here, is this whole thing. So do you see where we're going with this? Do you see where we're going with this? If this whole thing is congruent to itself, then what I'm actually forming here are two triangles. I'm forming this triangle do you see what I'm doing here with this? I'm forming this triangle. And then I'm forming the one over here, right? I'm forming the other triangle right here. I'm forming this one with congruent parts. And if I already know, look at what I know here. I know this. Now I know this. And I know this. What congruence method do I have here? It's kind of hard to see, but I'm just showing you. What do we have here? We have side angle side. Side angle side. So if I've shown that side angle side exists, I know that the triangles y, x, z, and of course this is saying, this is what I've marked in the bright green, y, x, z. That triangle right there is congruent to wxz, what I marked in the blue, wxz over here, wxz. Okay, they're congruent because of side angle side. And so here's our side angle side reason. And so this is side angle side. And then because of that, what can we do because of that? Well, this is a very important part of congruence in triangles. Cpctc. This stands for corresponding parts of congruent triangles are congruent. Oops. Corresponding parts of congruent triangles are congruent. Cpctc. Okay? So what that means is that we've shown these two triangles are congruent. So we have this triangle, and they're congruent. And we know that that is congruent to that, and that's congruent to that, and that's congruent to that. And so they're congruent. But each part, angle 1, angle 2, angle 3, side 1, 2, and 3, each part in this triangle is going to have a corresponding part over here that it's congruent to. And so each of these parts has to have, like if this is angle 1 here, right? That's angle 1. So this has to be angle 1. Those two corresponding angles have to be congruent because the whole triangle is congruent. So the really interesting, and the same thing for all the other sides and angles. So the interesting thing about congruence is that if you show congruence, then you have 3 sides and 3 angles. You have 3 sides and 3 angles in one triangle, and so this will be in the triangle number 1, and it maps directly. It shows you that there is a corresponding side, 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 and angle, angle, angle. And this is if. If congruent, then you have all of these things in the second triangle, and there is 1 for 1. Each side has a corresponding side in the other triangle that's congruent for all three sides and all three angles. Okay? So if you have congruence in triangles, then you have a corresponding part in each triangle that are congruent. And these are individual pieces. These are the three sides and the three angles. Okay? So because we've shown that the two triangles are congruent here, then we can jump to our proof statement, YZ, because again we're trying to show those congruent, right? YZ and WZ down here. But if we know that the whole triangle is congruent, then we can say that that part is congruent to that part because of Cpctc. Cpctc. Okay? Let's look at another example. Okay? And again, I have all of these reasons right here. We're just going to fill in the blanks. So given that AD is congruent to BC, AD is congruent to BC, and you can start to figure out how it best works for you to mark diagrams. So, for these videos, I find that I like coloring things in like this, but nobody really does that in geometry. We just use those little tick marks. We also know that AB, but sometimes this is easier to show things like this on a diagram for the purposes of teaching. And we know, so that was the first statement. And we know AB is congruent to DC. So AB, right here, AB, I hope you can tell this is green. AB is congruent to DC, right? These two are congruent. Okay? Well, we're trying to show that AD is parallel to BC. So we're trying to show that AD is parallel to BC. That's what we're trying to show. That'll be in our red statement. Okay, I'll do that always in red. So what do we know? What in the world do we know? We know AD is congruent to BC because it was given, and we know this is also a given, so we've used our two givens. Okay? Now we know that AC is congruent to AC, so that's here. That's this part right here. AC is congruent to itself because of the reflexive property. The reflexive property. So that's this one. That's that one. Okay? So now we have, what do we have? We have side, 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 right? Because each of the triangles has a blue side, a dark green side, and a light green side. So 1, 2, 3, side, side, side. So indeed, we have these two triangles are congruent, CAD and ACB, CAD and ACB, because of side, side, side. Okay, and then there's side, side, side coming off the list. And so if that's the same, if that's the deal, okay, then we know that DAC is DAC angle, DAC, so we're talking about this angle right there, is congruent to BCA, so this one right here, okay? And so we know those are congruent because this is definition of congruent triangles. I would even call that, I would call this as the Cpctc. So Cpctc, that's really what that's saying. And then we'll learn about this actually coming up next week. But if alternate interior angles are congruent, then the lines are parallel. We're going to learn about that next week. But, oh, excuse me, I meant to have red. We're going to learn about this thing called alternate interior angles next week. But basically, it doesn't matter. I'm just showing you this is a reason, right? This is a reason. We're going to learn what that word means, and then it shows, you know, this is an if-then statement, but here we go, lines are parallel, and that's exactly what we're trying to prove here. So this would be alternate interior angles, and of course then we're done with the proof. I want to look at one more. Actually, we're going to do a couple more. These are just so good. They're just so good. All right, so here we have a given. We got to write the given in, right? So the given is that ABCD is a p-gram parallelogram. Okay, that was that part right there. In a parallelogram, opposite sides are congruent. All right, this is the reason. This is the reason. So notice that we're trying to prove that this triangle ABE, where's my red? ABE, we're trying to show that this here, this triangle ABE is congruent to CDE. Okay. And again, you don't have to know all of these things we haven't learned yet, because I'm giving you all the possibilities, and so you just need to use your logic and match them up here. We'll eventually learn all these things throughout the year. Okay, in a parallelogram, opposite sides are congruent. Well, what would that mean down here? Excuse me. AE is congruent to EC. AE and EC, well, those aren't opposite sides. Those are part of the diagonals. Okay, so what about DE congruent to EB? No, that's still diagonals. What about AB and DC? Oh, AB and DC, right there. AB and DC. So that's that one. Opposite sides. AB congruent to DC. Okay, this is kind of showing it to you from the other side of the logic point of view. So now we know that AB is congruent to DC. We know those two lengths are congruent. Okay. In a parallelogram, diagonals bisect each other. We've got this once here and once here. So let's look at the diagonals. So AE is congruent to EC. AE is congruent to EC. That's that one. AE congruent to EC. And it doesn't matter which order you do these in. DE is congruent to EB. That's that one. DE is congruent to EB. And I could have written these in either order. I could have written those in either order, doesn't matter. And so what do I have? Well, I know that this is congruent to this, and I just showed that this is congruent to this, and so I have side, 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 side. I have a pencil mark side, a blue mark side, and a green mark side. I have a side, 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 and so I know that triangle ABE is congruent to triangle CDE because of side, side, side. So there's that. And of course I already used ABCD as a p-gram because that was a given. That was a given. Don't get confused about that. So that's all there is to that one. Okay? Let's do another one. Okay, so of course we're actually going to skip, like you can even do these with circles, which are really cool. We haven't learned much of the circle stuff yet, so we're not. This will be the last one we do in this video. But remember that an isosceles just means that you have two sides that are the same length, and a trapezoid is a quadrilateral that has one side of parallel sides. Actually, it could be just at least one. Some people like to classify rectangles as trapezoids, but I don't want to get caught up on the minutia there. So again, let's just go through this. Here I'm not telling you which order things go in, so these are possible statements and possible reasons. So look at what we're given. What are we given? We're given that DE is parallel to AV, as we would expect, because it looks like a trapezoid here, DE and AV. And then we know that triangle DAV. So, and sometimes this just takes some getting used to seeing all this stuff. DAV is congruent to EVA. So EVA. So you can start to think of like, well, what does all that mean? What does it imply? So, all right, so DE is parallel to AV, and of course that's a given. So we've used a given there, and we've used that statement up. Oops, I'm sorry. I should have all this on the screen. There's my bottom of my box. Okay. So there's a given. We've used a given. We used DE parallel to AV. We also know that triangle DAV is congruent to triangle EVA. That's that. It's also a given. And what are we going to say here? DAVE, Dave, is an isosceles trapezoid. That's the proof statement, so it gets the very last spot, right? So DAVE is isos trap. Boink. Gets that one out of the way, right? Okay. And then what do you think, looking out of these possible reasons, what do you think the reason that we're going to be able to say this is? Well, it's going to be because of the definition of isosceles trapezoid, right? We're showing that it is an isosceles trapezoid, and it's because of the definition. It's because what isosceles trapezoid means. So definition of isosceles trapezoid. So now all we have are two things here. So look at the last statement, and whenever you're doing a proof, you're just going one step at a time. You're going from here to 2, and then you're going from 2 to 3, and then you're going from 3 to 4, and then from 4 to 5. You just take it one step at a time. So looking at this statement, where do we go? What can we say? We have two triangles are congruent, and we can say that if they're congruent, then we know that they're corresponding sides. Look at DA. Here's this side. That side has to be congruent to this side of the blue congruent triangles. Okay, so DA is congruent to EV. And that was a given, I'm sorry. Because of Cpctc, and again, I'm just going to call this Cpctc instead of saying just definition of congruent triangles. So, DA congruent to EV. Alright. And so then if those are the same, so notice now we've shown that this is the same as that, and we have two that are parallel. So we indeed have the definition of an isosceles or rather of a trapezoid. Because we have a quadrilateral with two parallel sides, and so DAVE is a trap because of the definition of trap. And again, and you know, it's something like this. You could really even reverse these two steps. It just depends on how you want to do it. You can do it either way, because this step is based off of there, but so is this step. It's based off of there, so it really doesn't matter which one you do, because they're both coming off of that piece of information right there. Both steps 3 and 4, and I'm just going to write this down. Both steps 3 and 4 are based on step 2, so you could flip the order of them. You could flip the order of them because they're both just based on step 2. Okay?